Okay, now that we've been introduced to the T-model and have taken a look at a couple confidence intervals with the T-model, that leaves just one more piece of information for this chapter, and that's how to do a hypothesis test with the T-model. So kind of like the confidence intervals, the computations are a smidgen less messy because you're dealing with formulas like S over the square root of n instead of square root of PQ over n. So there's less numbers to mess with. And you don't have all those percentages usually floating around. So the mechanics typically are a little bit less messy. And you don't have to deal with anything like pulling counts. You will never pull counts in any hypothesis test for means in this class. So we're going to start with sort of a general problem and pull in how to think about writing hypotheses and how to think about errors, how to think about power of the test, those sorts of things that we've studied back in the last unit that still apply to hypothesis tests of any kind. They can apply to any kind of hypothesis test you ever do. So we're going to dig into those sorts of big idea things first, and then we'll end with actually running a full test from start to finish. We really already know the process. We're just refining some mechanics and a name of a test, and one condition is going to change. Everything else is what we've already practiced. So let's start right off with a medical question. During an angiogram, heart problems can be examined via a small tube called a catheter, threaded into the heart from a vein in the patient's leg. It's important that the company who manufactures the catheter maintain a diameter of 2 millimeters. Each day, quality control personnel make several measurements to test the null that the mean diameter of a catheter is 2 millimeters against an alternative that it's not 2 millimeters at a significance level of alpha equals 5%. If they discover a problem, they will stop the manufacturing process until it is corrected. Okay, so we skip straight to questions, and we'll start with this next slide, which poses the question, is this a one-sided or two-sided test, and why is this important in the context of the problem? So if I look at my alternative hypothesis, this is how I know what kind of test I have, one-tailed or two-tailed. Not equal to is the same thing as greater than or less than, which means a catheter that's too small is a problem. A catheter that's too large is still a problem. So anything too small or too big is going to be an issue in the real world. So this is a two-sided test. So it's two-sided. If a catheter has a diameter that is either too small or too that's the wrong two. I think my mind is wondering, too small or too large. It will not work properly. If it's too small, then it probably won't do the job it's meant to do. If it's too large, will it even fit through a patient's vein? Will it could potentially hurt a patient, could do a great deal of harm. So it's important that we keep it within a window of acceptable diameter. It doesn't have to be a long paragraph, it just has to be something in context that makes sense. So if you're asked questions such as this on the AP exam, just make some sense of the problem, say something in context that's a reasonable issue. Make sure everything's in context. Okay, done with that one. Let's move on. Explain in this context what happens if the quality control people commit a type 1 error. Okay, so this is where I kind of go off to the side and think about it first. So in a type 1 error, the null is true and we reject it. Okay, so if the null is true, that means the catheters really are at a mean diameter of 2 millimeters. Okay, so let's start with that. The catheters are actually being manufactured with the correct diameter, but, all right, if we reject it, that means we don't think they're correct diameter. But quality control personnel, we'll just call them quality control, believes that the catheters are incorrect and stops production. So we stop the machine and we do some work on the machine to make a correction unnecessarily. So we halt production. That holds up the works. But worse than that, we may throw away a large quantity of catheters that have just been manufactured that are actually good catheters, but we throw them away thinking that they're not good catheters. So this quality control personnel has pulled some catheters from the assembly line to test, to check, to measure, and has come up with a sample that does not accurately represent what's really coming off the machine, thinks they're too small or thinks they're too large, and they throw those out and waste materials, throw away money, and hospitals don't get the tools they need quite as quickly, possibly because production has been held up. All sorts of things you could talk about that could go wrong with this question. Okay, moving right along. What if we get a type 2 error? Explain what happens. Okay, in the type 2 error, the null, which says the diameter is really 2 millimeters, is false. In other words, the truth is the machine is out of, I can't say the word, out of calibration, and it's not producing the right diameter. But we fail to reject, so quality control personnel doesn't catch the mistake, and bad catheters get packaged and sent to hospitals. Okay, so let's write that out. The catheters are actually being produced with incorrect diameters, but the quality control believes that they are correct. We continue to manufacture bad products and potentially send bad catheters to hospitals. This isn't as costly a mistake on the front end because we're not throwing things away that we've manufactured, but it could be a really big mistake on the back end when the hospital gets catheters that don't work correctly. So then the manufacturer is probably going to not only get, they're going to lose money because they're going to get these catheters back, or they may even get a lawsuit. They could lose business, So in the realm of manufacturing, this is probably the bigger error. Okay, so again, just general things. It's exactly the same reasoning that we used when we were talking about proportions. Nothing's changing there. The only thing that changes when we talk about averages or means or quantitative data is the fact that we're using units and we're using different types of numbers, not percentages of successes. Everything else is the same business as we had before. We're just practicing that business again. Okay. If the significance level is changed to 1%, will the probability of a type 2 error increase, decrease, or stay the same? So here's what we learned in previous chapters. Type 1 error and alpha are related to each other. The probability of type 1 error is alpha. So if alpha goes down, so we were at a 5% alpha level, so alpha has decreased, which means type 1 error has also decreased. If type 1 error decreases, then type 2 error must increase. So it's going to increase. It didn't ask us to explain how we know or why we know. Our thinking strategy is over here in the corner. So we're done with that one. Okay, now review of power of the test. Okay, so the power of the test is a probability. It's the probability I'm having some trouble with my spelling this morning. So it's the probability of correctly rejecting a false null. This is the send the guilty guy to prison. Okay, that's what we're after. The whole purpose of testing is to make sure that we are not making bad products and shipping them off to hospitals by mistake. So it's the probability of correctly identifying catheters that are being produced with incorrect diameters. This is the purpose of quality control in a manufacturing plant. Quality control's job is to catch the bad stuff, because not catching the bad stuff is a very costly mistake in their world. So you hire people whose sole job is quality control. Their job is to find the bad stuff. They have the power in the plant. Okay, so short answers, just reviewing all these big concepts, good to keep those fresh. So one more question about this, and then we will move into a full-fledged hypothesis test, and that will finish this section. Suppose the manufacturing process is slipping out of proper adjustment, which means that null of 2 millimeters being the truth is false. It's slipping. Diameters are not 2 millimeters on average. As the actual mean diameter of the catheters produced gets farther and farther above the desired 2 millimeters, so the machine is producing catheters that are just a little bit too big, and they get bigger and bigger, will the power of the quality control test increase, decrease, or remain the same? Okay, so if they're actually slipping out of alignment, then that means when the quality control personnel is testing samples of product, there will be bad product in the sample, more bad product in the sample than there normally is. So that means your personnel should be more likely to catch mistakes because you have more mistakes. So power should increase. Okay, we are more likely to reject the null if catheters are actually not averaging 2 millimeter diameters. You should have more evidence that things are wrong, and therefore you should be more likely to catch the fact that things are wrong. Second question, what would they do to improve the power of the test? Well, okay, there are multiple things to improve power. They could, let's see, what would improve power? You could increase your alpha level, because increasing the alpha level makes you more likely to reject. So they could increase alpha or. But of course, increasing alpha would make them more likely to get a type 1 error, which makes them more likely to throw away good catheters. We don't really want to do that if we don't have to. Or, better yet, increase the sample size. Look at more catheters. The more you check, the more likely you should be able to discover that you have some bad stuff in there. You should be more likely to get the truth with a larger sample. And the truth is, they aren't 2 millimeters anymore. Okay, so now that we've had a chance to kind of refresh all of those things concerning power of the test, errors that are associated with tests, now let's actually do a test. One test. So let's talk cars this time. Company with a large fleet of cars hopes to keep gasoline costs down and sets a goal of attaining a fleet average of at least 26 miles per gallon. Okay, so that means 26 is sort of their cutoff, their limit. So that's probably going to give me a null starting point, a null average. Okay, so this is going to be my null hypothesis mean. And I'm not worried about the at least and the null. We are always going to say equal to. But at least means we want 26 or more, which means we would have a problem if we were achieving less. So that's already kind of hinting at what that alternative should look like. To see if the goal is being met, they check the gasoline usage for 50 company trips chosen at random. That sounds like a sample size. So 50 is my N. And finding a mean, at random, that's good because I'm going to need that. Finding a mean of 25.02 miles per gallon. Now this is the mean of that sample. So this is Y bar. So this 26 up here is going to be a mu, Y bar from the sample. And a standard deviation of 4.83 miles per gallon. That's the standard deviation of this sample 50 trips. So this is going to be my S of X or S of Y or just S. Is this strong evidence? Okay, that means run a hypothesis test. That they have failed to attain their fuel economy goal and test an appropriate hypothesis. Okay, so first thing we do is write some hypotheses. So the status quo was we want to achieve a minimum of 26, so 26 is our null hypothesis mean. And if it drops below that, they have failed to attain their goal. So that's going to be our alternative. So this is a one-tailed test. We only care if our fuel economy is too low. Better gas mileage is a good thing. That's not a problem. Alright, so let's scroll down here to the hypotheses. So first of all, we need to define our parameter. What are we measuring? We're measuring the mean or average fuel economy. Okay, so let mu equal the average miles per gallon of all cars in the fleet. Okay, remember, hypotheses are about the entire population. which means there should be no Y bars floating around in your hypotheses, just like there should have been no P hats in your hypotheses. You put Y bars here, you're not going to get any credit for your hypotheses. So you're making a prediction about the population of everything in the whole fleet. So all cars, let's make sure we put that in our description of our parameter every single time. So the null is that mean average, or that mean miles per gallon is 26 miles per gallon. Make sure you include your units there. It's just a good habit. Alternative is that we are not attaining that, which means our fuel efficiency is too low. So the mean is less than 26 miles per gallon. So this is a one-tailed lower tail test. The only difference in these hypotheses and what we wrote in the last chapters was we're talking about mu's instead of p's. We're in mean world, not proportion world. Okay, second step is to check conditions or assumptions. So let's move on to that page. So 3 conditions. Since we just have one sample, we're back to 3 conditions. The first condition, as always, is our randomness, and they told us we had 50 random trips chosen from the fleet. So the 50 trips in the sample were random. You're not assuming this, you know this. They told you so. They spelled it out. Say it's true because you know it's true. Check. 2. 50 trips is less than 10% of all trips. Well, it said they had a large fleet of cars, and even if they just had 10 cars and each of those cars made 50 trips, you'd have 500 trips. But they have a large fleet. So 50 should be definitely less than 10% of all possible trips. You could argue that, or you could offer that the gas mileage for each trip is an independent event. I think maybe 10% is just quicker to argue. So we're going to assume, pretty sure, that 50 trips is less than 10% of all trips for a large fleet of cars. So I'm going to go back and argue. You said you had a large fleet, so we're pretty sure that it's going to take more than 500 trips for this fleet in the whole population of trips. Definitely reasonable. Last but not least is the sample size condition. Our best hope always is that we have a sample size of at least 30. We have 50. That's fabulous. So 50 is larger than 30. So central limit theorem says we have a normal sampling distribution. Yay. No graphs to draw. Not that we could anyway since we don't have the data. But definitely we can be sure that it is a nearly normal distribution. So, true, true, true. A T-model can be used, and we will do a one sample T test. Okay, be careful not to say T interval. This is a test. Be careful not to say one proportion. Hopefully it's a habit by now to talk about one proportion tests and two proportion tests, but we are not in proportion world anymore. So we change that word to sample when we get into means. Alright, we're halfway there. So now we get into mechanics. Just like before, we start with the picture of a normal model. So the picture of all possible averages of all possible 50 fleet samples would have mean miles per gallon Y bar. This is the picture of all possible Y bars from all possible random samples of 50 trips. So there's Y bars floating around under this curve. Our Y bar is in there somewhere. We're trying to find out where it is and if it's unusual enough to doubt the null hypothesis that we started with. Okay, so let's talk some notation. So the first thing we need is the mean of this distribution of samples. So that's the mean of the Y bars. So we're not in p-hat world anymore. We're in Y bar world now. And in our blue books, we have on that second page of formulas the mean and standard deviation for the distribution of means. And it says the mu of Y bar is equal to mu itself, which is 26 miles per gallon. It's the mean that we're assuming in our null hypothesis. Okay? So we just changed from p-hats to Y bars. And instead of a true p, we have a true mean. So the middle of this curve should be 26 miles per gallon. The standard error of Y bar, now we can't do a standard deviation here because we're having to use the standard deviation of the sample because we don't know standard deviation of the population. So we actually aren't going to use a sigma here because we can't compute a sigma unless we know the true standard deviation of the population, and we will never know that. So the best we can do in a hypothesis test is standard error of the Y bars, or you could call S of Y bars. Okay? So use an S, not a sigma, if you want a shortened version. Now, the formula in the blue book says this is S of the sample over square root of n. S over square root of n. And the standard deviation of our sample was 4.83. We're going to divide by square root of the sample size, which is 50. And when we do that computation, we come up with a standard error of about 0.683. Now, like we did with proportions, you can skip writing this down, and go straight to the z-score, or actually now it's a t-score because we're in t-world. This is a t-model, not a z-model, slightly different. So if you skip to the t-score calculation and you embed these numbers, these calculations in that formula, you can do a one-step computation in the mechanics and have all of your bases covered. So what do we want to be able to show? Well, we want to be able to show how to calculate the t-score. That's our big deal. And t's come with something called a degree of freedom. And that degrees of freedom has to be communicated somewhere in this problem. If you don't tell somewhere in these mechanics what your degrees of freedom are, or squeeze it into the conclusion, which I think is a little more cumbersome, then there's a chance you're not going to get your full points here. So we can do one of two things. We can anywhere in the picture or anywhere in the mechanics state that the degrees of freedom is 49. It's one less than the sample size. Or we can put a subscript on our t and just make it a habit, and that will cover our backside. If there's the subscript 49 on your t, you're communicating to your reader that you know that this has 49 degrees of freedom, and then it's covered. You don't have to write it anywhere else. So again, your t-score calculation holds all the important information. So it holds the fact that it's called a t-score, degrees of freedom of 49. In the numerator we have observed minus expected mean. Now the observed mean is the piece of information that we have not yet used. That's your Y bar. That's what we observed in our sample. And if we go back and look at our original problem, we had a sample mean of 25.02. That is the only place in this whole problem you're ever going to see the sample. Minus the expected mean, well, we expect it to be 26 in a perfect world where the null is true. So minus the 26 over the standard error, which you can put a 0.683 here, or you can put 4.83 divided by square root of 50. Now, if you show this covers all the information. And if you show this t-score calculation with the degrees of freedom and your formula embedded for your standard error, and you don't write anything else down in this picture, that will get you full credit. But you have to show this somewhere. You can't just write down 0.683 and not show where that came from. So you either make it a separate step or you embed it. This is your best bet for getting all of your point value right there. Okay, so when we crunch that number, we can either put it into the calculator just the way it looks, or we can actually run a test, and if we run the test on the calculator will give us that number. So let's take a look at that. So, a couple of options. Well, actually, let me hold off on taking a look at that. Let's do one more quick calculator thing first. I'm going to go ahead and tell you that this turns out to be about negative 1.43. So that we can do one more thing with the calculator before we actually run the full-fledged test. I need a p-value. So 1.43 negative, 1.43 negative, it's about here. This is where 25.02 hits. And since we had an alternative hypothesis that said we want to know if it's less than, we're going to shade to the left. If I want to know that area, that's my p-value. And to get that area, I need the probability of a t-score less than 49 degrees of freedom, 25 point, oh, nope, Mr. Rice, nope, back up, that's not your t-score, that's your raw mean. Let me back up, make that better. A t-score of less than negative 1.43. Okay, so we deal with this exactly the way we did z's. It's the same work that we did with z's, other than the fact that we have a different formula for standard error. So when I do calculator work, and I go to menu, either probability or statistics, and number 5 for distributions, I need that TCDF to calculate that p-value. So TCDF, and you'll notice that you don't have the option to put in a mean and a standard deviation here, which means you have to have a t-score. You cannot use 25.02. It will not take the raw mean in units. So we have a lower bound of negative infinity, an upper bound of negative 1.43, degrees of freedom are 49, and if you forget to write it down somewhere here before you pick up your calculator, there's your reminder that it needs to be on your paper somewhere. And then if we press OK, they tell us that that's about 0.0795. Okay, so there's all the mechanics. Bare minimum is to show the t-score calculation and to report your p-value. Now, other options. You could actually run the test with your calculator and not have to do the computation for the t-score and the computation to get a p-value in 2 separate steps. You can get them both at the same time if you'll run the test. So let's take a quick look at that. If we go to menu, statistics this time, number 6, and stat tests at the bottom, number 7. We do not have a one sample t-test in here. It doesn't exist. What we have is just a t-test. And the t-test works for both a one sampled and some paired samples that we're going to use later. So it's just number 2, the t-test. We don't have the data. We did look at data with a confidence interval on Monday's lesson. So it works the same way. If you actually have the raw data, put it in a spreadsheet and work through the same set of steps. That's the only difference, is you have to put your data in the spreadsheet and you might have to do a quick histogram in your conditions check. We're going to change the data to stats because we have summary statistics to work with on this problem. And then it's going to ask us for some information, the first of which is mu sub 0. This is mu from the null hypothesis. We were claiming 26 miles per gallon. So that's the claim from the null. X bar is the same thing as Y bar. That's our sample mean. That's 25.02. S of X is the standard deviation from the sample. That was the 4.83. N is sample size of 50. It can find out for itself that it has 49 degrees of freedom. The alternative hypothesis was a less than, so let's change that to the null is, the true mean is less than that argued in the null. So that always should match the direction we have things in the alternative hypothesis. And click on OK. And we get some important information, including but not limited to a t-value of negative 1.43. So that matches what I had here. So if you run the test on your calculator after you get this set up, then you get everything else all in one fell swoop. You only have to push one set of buttons. So you get your t-score, you just write it down, and then you get your p-value. It's a little different here because there was no round off error here that I did have here. So 0.79 is what the calculator is going to give us. Nobody's going to fuss about this on the AP exam. If there's some decimal differences, they're going to assume that you rounded differently. It's not a big deal if you've shown your work. Degrees of freedom are 49. It reiterates the mean, standard deviation, and sample size. But the biggies is it gives us the t-score and the p-value so we can get this computation and this computation all at one time. Okay, last but not least, write a conclusion. We are almost finished. So, with a p-value of 0.079-ish, that's bigger than 5%, bigger than any reasonable alpha level. That's not interesting. It's not low enough to be interesting, so we are not going to reject. We will fail to reject the null hypothesis at an alpha level of anything reasonable here would work. I'm just going to stick with my usual 5%. There is little evidence that, let's go back and look at their wording, they have failed to attain their fuel economy goal. Okay, so I'm just going to repeat back their own words to them. That's the safest way to make sure your context is correct. And the only thing that could possibly happen that would be different than what we just did is if they give you actual raw data, you put it in a spreadsheet in your calculator, and pretty much everything else is the same. You run a test on your calculator with your data, and it's going to give you all the numbers that you need. It's going to give you the mean of your sample. It's going to be give you the standard deviation of your sample. All the numbers you need for your hypothesis test mechanics will be embedded in the page. Everything you need is going to be right here. So you can have your mean, you can have your standard deviation, everything you need to put in your formulas and your mechanics will be reported. So this is one case where if you have the data, you're going to want to put it in your calculator and actually run the test before you set up your equations in your mechanics, because you're going to need these summary statistics. So you kind of work backwards and get your calculations done before you write everything down. Okay, that is it for chapter 22. So you have a day 3 assignment that you can work on for now. There will not be additional notes tomorrow. We've covered all the notes. Tomorrow will just be some extra practice. So be looking for a quiz over chapter 22 on Thursday, and hopefully by then I will have the tests graded from Unit 5. Just working on those, and hopefully not take me more than a couple days to finish them up. So hope y'all are healthy and doing well, and that's it for now.